Hello class, and welcome to section 9.7, which is about linear and nonlinear functions. Our goal today is to be able to use different formats to determine whether a function is linear or not. First thing I want you to do is look at this graph and describe the shape of the graph. Try and think of one word to describe the shape of the graph. The best word to describe the shape of this graph is curved. This is an example of a nonlinear function. When we have something that is nonlinear, it's going to go up in a pattern that is not a straight line. So as you can see, it starts at the bottom here, and then it curves up as opposed to a linear graph, which would have started at this first point and gone straight through that last point. The other thing I want you to look at is the rate of change on the graph. Remember that the rate of change is our change in y over change in x, so how much we're going up versus how much we're going over. I want you to decide if that value is constant between all of the different pairs of points. The answer for that is no. If we look at our rate of change here, let's say that this is 20 and this, or let's say it's about 21 and this is about 41. We've gone up by 40 while we've gone over 2 years. But if we look at this next pair, if we go from 41 to this is probably about 70, we're going up by about 29 and then over by 2 years. So we're going, as the line keeps going, we're going up by more and more each time we go over. So that rate of change is not constant. That's one of the characteristics of something that is non-linear. So a nonlinear function does not have a constant rate of change, which is what we just discussed in the last part of that last slide. The graph is going to be curved, and if there's a variable in the equation, it's going to have an exponent other than the number 1. So for example, if we had a nonlinear function, the equation for that graph might be, for example, y equals x to the second power. So there's something other than 1 in the exponent if you have one. If you have a linear function, you aren't going to see that variable. So for example, we know that y equals 3x plus 7 is a linear function because we learned about that in chapter 8. That's y equals mx plus b. That's going to form a line. And the exponent on these variables is I would put in a 1 as the exponent for that x. So the first thing we're going to do is we're going to look at graphs. I want you to take a minute and decide which of these 4 graphs is linear and which is nonlinear, and make sure you give a reason. So the first graph is nonlinear because we have that curve right here in the middle. The second one is linear, it's a straight line. Third one is nonlinear, again we have that curve. And then our last one, also nonlinear because we have the curve. Next thing we're going to do is look at equations. So again, when we're looking at equations, we're looking at the exponents on the variable. So in this one, we don't have it solved for y yet, so we're going to go ahead and we're going to subtract 3x on both sides to get it into that y equals mx plus b format if we can. So we've got y equals negative 3x minus 7. Looking at our exponent here, we've got an exponent of 1. So this would be a linear function. And the reason for that would be that exponent is 1. So we've got our exponent of 1. If I come over to this next one here, we've got y equals 2x to the second power. So in this case, when we look at that exponent up here, we've got an exponent of 2. So this is going to be nonlinear. And our reason for that is an exponent. The exponent is 2. So I want you to go ahead and identify whether these last two are linear or nonlinear and give a reason. The third one is nonlinear because the exponent is x, so it's not even a number. The exponent is a variable. And then the last one is linear because that exponent, if I put it into the equation, would be 1. Last thing we're going to look at is how we can determine this using tables. So if I come over here to this first table, I'm going to look, and we want the rate of change to be constant, which means our differential between the x's and the y's should be constant. So I come over and I look at the x's, and to get from 1 to 2, I added 1. To get from 2 to 3, again, I added 1. To get from 3 to 4, I added 1. So our x's are good. The x change is constant. I'm going up by 1 every time. When we come over to the y side, I've got -5 to -20, which means I went down 15. Then I've got to get from -20 to -45, and for that, I have to go down -25. Then to get from -45 down to -80, I have to go down 35. So even though my x's are constant, my y rate of change is not. So this would be an example of a nonlinear function if you are looking at it in a table. And your reason for this would be not, and then I'm going to abbreviate it to CROC, which stands for constant rate of change. If you want to write out the words constant rate of change, you can, or you can just use the abbreviation CROC. Now we're going to look at this next one now. Again, 2 to 4, that's going to be up 2, 4 to 6, up 2, 6 to 8, up 2. So we're good with our x values. That's a constant rate right now. Then we're going to come over to our y's. 1 to 2 is 1, 2 to 3 is 1, 3 to 4 is 1. So my x's are constant and my y's are constant, which means this is a linear function because it has a constant rate of change. Go ahead and decide if the last two are linear or nonlinear on your own. These last two, the first one is nonlinear. We're going up by 1 for the x's and different numbers for the y's, so it's not constant rate of change. And then for my second one, we are going up by 3 and up by 4, so we do have a constant rate of change. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.